Dear students, let us solve one problem on economic operation schedule considering transmission losses. Determine the economic operation schedule of a two-plant system to meet a load demand of 160 megawatt. Load demand given is 160 megawatt. The incremental fuel cost and loss coefficients of the two plants are given below. We have two plant system and total demand is 160 megawatt. The incremental fuel cost of plant 1, that is dC1 upon dPg1, is given as 0.01 Pg1 plus 2 rupees per megawatt hour. And the incremental fuel cost of the second plant 2, is given as dC2 upon dPg2 is equal to 0.01 Pg2 plus 1.5 rupees per megawatt hour. Earlier we have studied in detail what are these incremental fuel cost. If you are not aware, then you can watch my previous videos on this topic, part 1 and part 2, economic operation of power system. And the loss coefficients for the two plant system, obviously we will have four coefficients: B11, B12, B21 and B22. And these two coefficients B12 and B21 between line 1 and 2 are same. So these are the values given. We need to get the economic operation schedule of the two plants, that is economic values of optimal values of Pg1 and Pg2 to get the best benefit. So the steps have already been discussed in the previous lecture. You can go through part 2 of this series. So what are the steps? Step number 1, first assume suitable value of lambda. Assume lambda. So lambda is equal to, in that step it has been discussed that it must be greater than the largest intercept of the incremental cost of the plants. So here we have just two plant system, plant 1 and plant 2, and these two are the incremental fuel cost equations of the two plants. So the intercept of this plant 1, incremental fuel cost of plant 1, is having this relation. So this is the intercept, this is 2, and the intercept of the second plant is 1.5. So it must be greater than 2. So assume any suitable value. Let us say, let us say lambda is equal to greater than 2. This is 1.5, 2.55. You can take any value. Initially you have to take any value. So let us take it. Now equate these two. See the steps given in the previous lecture. So what is the next step? So this must be as per the equal incremental criteria. These two will be equal to this lambda, that is 0.01 Pg1 plus 2 from incremental fuel cost equation of first plant will be equal to this lambda, that is 2.55, and this will also be equal to the incremental fuel cost of second plant is this. So equate this 0.01 this Pg2 plus 1.5 and solve for Pg1 and Pg2. So once you will solve this, so you will get Pg1 solved yourself, and Pg2 is equal to 55 megawatt. Solve this is equal to this, and Pg2 is equal to this. So this one will be equal to 2.55 minus 1.5. So finally Pg2 will be equal to 105 megawatt. And in previous lecture we have derived the coordination equation as Pgi is equal to 1 minus Bi upon lambda minus. So for two plant system we have I is equal to 1 and 2 only, and this relation we have already derived in the previous lecture. So if you are not aware of this derivation, you can go through that lecture. So now in this problem we have two plant systems, so I will be 1 to 2. So write expressions for Pg1 and Pg2. So from here we may write expression for Pg1. Pg1 is equal to 1 minus B1 upon lambda. I is 1 here, Pgi, so I is 1, put Bi is equal to B1 minus. So we have just two plant system, so I is 1 here, J should not be equal to I, so J will not be equal to 1 for Pg1, so J will start from, and this will be 1 to K. So K is number of plants, so here we are having K2. So for J is equal to 1, I is equal to 1, J will not be equal to 1, so J will be 2 and up to 2 because K is 2 here. So put J is equal to 2 here, so this one will be minus 2B, I is 1, 2B, J is 2, so 2B 1 2, and PG, J is 2, so PG 2 upon I is 1, so A1 upon lambda plus 2 B11. So this can further be written as 1 minus, so B1 upon lambda. So B1 is, see the incremental fuel cost, del C1 upon del Pg1. So this is B1 intercept and this is A1. Similarly, this is A2 and this is B2 1.5. Substitute the values. So B1 is 2 upon lambda, we have assumed 2.55 minus 2 times B12 is given. So B12 and B21 both are same in magnitude and with negative sign, so here we will put plus, and this one will be equal to 0.0005 Pg2, so into Pg2 upon A1, just we have seen A1 is equal to 0.01 here, from here 0.01, B1 is also 0.01 in this problem. So 0.01 upon lambda, we have assumed 2.55 plus 2 into B11 is given, loss coefficient 0.0015 per megawatt. So this is equal to 0.0015. So this can further be written as is equal to, so Pg1 will be this one, 0.215686 plus 0.001 Pg2 upon 0.00692156. You can solve it yourself, you can simplify it and you can verify it. So similarly for Pg2, similar to that, using that equation we may write Pg2 is equal to 1 minus B2 upon lambda. Now we will have 1 minus B2 upon lambda minus 2 B21 and B12 are same, so write here B21 or B12, Pg1 here because I is not equal to J in that condition, upon A2 upon lambda because we are writing for Pg2. So for Pg2 we'll have A2 upon lambda plus 2B22. So after substituting the values, we will write 1 minus. So what is B2? B2 is also 0.01. Okay, here we are having intercept as 1.5. So this is B2, 1.5, and this 0.01 is A2. A1, B1, A2, B2. So A2 we are having 0.01 and B2 we are having 1.5. So right here 1.5 upon assumed value of lambda is 2.55 and B12, B21 are same. So B12 value is 0.0005 Pg1. So I is 1 here. Basically this is Pg1. Pg1 upon A2. A2 and A1 are same, 0.01 upon lambda is 2.55 plus 2 times B22. So B22 is given as 0.0025. 0.0025. So after simplifying, we will get Pg2 in terms of Pg1 as, so we have the equations for Pg1 and Pg2. This is for Pg2, Pg1, and similarly we have this equation for Pg2. So these two equations will be solved iteratively. So starting with some values of Pg2 which we have already calculated here. So we have calculated the values of Pg2 as 105 megawatt and Pg1 55 megawatt. So you can start from any value of Pg2 or Pg1. So let us start with Pg2 is equal to 105 megawatt. So once you put Pg2 is equal to 1.5 megawatt, you will get value of Pg1, and that obtained value of Pg1 will be substituted here and we will evaluate Pg2. Again that's evaluated value of Pg2 will be substituted here and we will evaluate Pg1, and so on. Again substitute here, obtain Pg2. So these two equations will be solved iteratively as already discussed in the steps of the previous lecture. So starting with that value of Pg2, that is 0 megawatt, 5 megawatt, 105 megawatt. So we will have the powers right here for Pg1 and for Pg2. So put value of Pg2 as 105 here and solve it, evaluate Pg1. So you can check yourself. I am writing directly the value. So for that value of Pg2 105 megawatt, the calculated value of Pg1 is 46.33 megawatt. Now substitute this value of Pg1 46.33 megawatt in the equation of Pg2 here. Pg1 will be equal to now the calculated value of this Pg1, and then we will obtain Pg2 is equal to this. Verify yourself, you can calculate. Now we have this updated value of Pg1 and Pg2. Initially we have taken these two values by that equation by assuming initial value of lambda, and we have equated this equal incremental cost criteria and we have obtained Pg1, Pg2. Now those values are updated and these are the updated values Pg1 and Pg2. Similarly for next iteration, again calculate Pg1 So this Pg1 will be calculated by substituting Pg2 as 51.35 megawatt. So we will get Pg1 as this 38.58 megawatt. Now substitute this value of Pg1 here and we will get Pg2 50.48 megawatt and so on. That is again calculate Pg1 by substituting this 50.48 megawatt here Pg2 and that Pg1 is coming out to be 38.48 megawatt. Again substitute this value of Pg1 here in the equation of Pg2 and we will obtain Pg2 as 50.46 megawatt. So we are getting the pairs of Pg1 and Pg2 more and more updated in each iteration. Now we can observe the total demand is 160 megawatt. So total generations, that is, we have two plant systems, so total generations will be Pg1 plus Pg2. So this sum Pg1 plus Pg2 should be greater than demand 160 megawatt. So we get this 38 and 50 lesser than 100 megawatt. So it is not possible. We can write Pg1 and Pg2 is very less than PD demand on the system. Ideally, sum of these two generations Pg1 and Pg2 must be equal to the total demand plus losses occurring in the system. So using the steps, we can what should be our next step? If total generations are very less than demand, obviously increase the value of lambda. So let the increasing value of lambda be, so earlier we assumed lambda as 2.55, so increase it. Since these two generations are very less than PD, so we will increment more. So let us take now lambda is equal to 3.75. Let us assume that. With this assumed value of lambda, the coordination equations are Pg1 is equal to, right here using similar procedure, and Pg2 is equal to, we have already written Pg1 and Pg2. So we have increased lambda. So now we will get different such coordination equations Pg1 and Pg2. So just verify it at your end. Now powers from these two coordination equations are the updated coordination equations. So Pg1, this should be Pg2. So from these two coordination equations, we will get Pg1 and Pg2 as these pairs. So we can observe from here that some of these two generations Pg1 and Pg2 are more than demand 160 megawatt. So some losses will be there. So now we need to calculate losses. So we know that PL, earlier we have derived the relation for loss. So PL will be equal to summation K equal to 1 to K, where K is total number of plants, summation K equal to N to K, or better we may write, take K is total number of plants, so better write I. So I is equal to, or M is equal to 1, whatever you want. So better write here the same notation which we have used in previous. M is equal to 1 to K, and put here N is equal to 1 to K. So PG, we have taken M, so write here M. B Mn, Mn, and PG, the second one is N. We have two plant system, K is 2 here. So for our system, substituting the value of B 1 2 1 1 2 2 like that. So we will write PL for two plant system, M is equal to 1 to 2, N is equal to 1 to 2, and this one. So this will be equal to Pg1, M is 1, so Pg1, this 1, I is 1 to 1, so B1 1, and again Pg1, so N is 1, so directly right here a square. Similarly, we will get Pg2 square B22 and plus 1 2 and 2 1 are same, so write here twice for two plant system, B12 Pg1 and Pg2. So after substituting the values, we have Pg1 is equal to 98.42 and Pg2 is equal to 91.09. The values of loss coefficients B11, B22, B12 are given in the problem. So directly we can get the values as 26.31 megawatt. Just verify it yourself. Put the values and check. So now we have the generations from two plants Pg1 and Pg2 as this 98.42 Pg1 and Pg2 as 91.09, and corresponding losses. Total loss is 26.31 megawatt. So these are the sum of generations and load we know, and this is the loss. So we will compare whether we are generating enough quantity to take care of load and losses. We need not to generate more than the required, otherwise that solution will not be economical. So just check the magnitude of Pg1 plus Pg2 minus obviously loss, PL, and load, total demand. So this magnitude is coming out to be 3.2 megawatt. I need to check it. Okay, so we can observe that this time by incrementing this lambda from previous value up to this. Why did we increase this value of lambda? Because earlier the assumed value of lambda was such that the corresponding generations were very less than the demand. These were the generations, the last pair, very less than the demand. So we increased the value of lambda as 3.75. The corresponding generations we have obtained as 98.42 and 91.09, and the corresponding loss is this. So now we are getting more generation than the demand plus loss. So this is not economical. We are investing excess money on excess generation than the required. That solution will not be economical, although we can fulfill the requirement, but we have some excess energy. So we need to reduce the value of lambda. Therefore, decrease lambda. Let the new value of lambda be, let us assume 3.69. So for this assumed value of lambda 3.69, the coordination equations are now Pg1 is equal to, write using the same procedure, write the values of Pg1 and Pg2. So starting for Pg2 is equal to 219 megawatt. From where this 219 came? Now we have decreased lambda to 3.69. So for this new value of lambda, again calculate PG1 and PG2 using equal incremental cost criteria as we started earlier. So for this value of PG2, again repeat the same procedure. So starting with PG2 is equal to this, put here, calculate PG1, again that calculated value will be substituted here and PG2 will be calculated. So during various iterations, the calculated values of PG1 and PG2 are, just calculate yourself and verify with these values. So the calculated values of PG1 and PG2 during various iterations are obtained as shown. Now calculate loss and compare with these total generations, this PG1 plus PG2, whether coming out to be equal to loss plus demand or lesser than that or more than that. So this PL will be calculated using the same formula. So I am writing directly the values, just calculate yourself. 25.19 megawatt. Now check the magnitude of PG1 plus PG2 minus PL, this loss, minus demand PD is equal to this. PG1 is 95.86 plus PG2 is 89.41, loss is 25.19 minus 160 megawatt. This was the demand. So this is coming out to be 0.08. So this is lesser than the tolerance. Say tolerance is 0.1. Let us take it 0.1 megawatt. You can tolerate, you can set it. So stop here, stop here. You have obtained your solution. So these are the solutions. PG1 is this, PG1 is this in megawatt. No need to worry, just for learning purpose we need to explain these calculations. These calculations are basically done using computer programs. You need to just develop the algorithm and finally you will get the optimal solution. Now let us solve one more problem. Problem second. This problem was asked in GATE 2012. So second problem, problem 2. The figure shows a two generator system supplying a load of PD is equal to 40 megawatt. Two generator system is there connected at bus 2. This is bus 2, this is bus 1. The fuel costs of generators G1 and G2 respectively are C1 PG1 is equal to 10,000 rupees per megawatt hour and C2, that is function of PG2, is 12,500 rupees per megawatt hour. And the loss in the line is P loss. This is given by, loss formula is given by 0.05 PG1 square. Obviously losses will occur because of this PG1. PG1 is being transmitted through this line till this location, and PG2 is directly feeding the load, so no transmission loss will be there. Obviously it is obvious that the equation should be like that, something like that. So it is given P loss is 0.5 PG1 square in per unit, where the loss coefficient is specified in per unit on a 100 MVA base. So all calculations will be done in per unit, and once the calculation is done we can get the actual value. We know the relationship between actual value, base values and per unit. Find the most economic power generation schedule. This question was asked in GATE 2012. GATE 2012. You can verify it. So 4 options were there. I have omitted the options directly. I have added this line. Find the most economic power generation schedule. The same question was asked here. So for one more thing, see the units rupees per megawatt hour. So these are basically incremental fuel costs, not cost. The unit of cost will be in rupees. So once we are getting DCI upon DPGI, so that will be incremental, and power is in megawatt, so that will be in rupees. Cost will be in rupees per hour. We have seen in our first lecture, first part, where we have plotted the fuel cost rupees per watt per hour versus this on x-axis power generations, like that, if you remember, something like that. Here the units were rupees per hour, and here watt or kilowatt powers were there, right? PG min, PG max, like that, if you remember. So just observe the units. If units are like that, so those are cost. Our first derivative of this will give the incremental fuel cost, so that will become rupees per hour upon megawatt, that is rupees per megawatt hour. So these are the incremental fuel cost of the two plants, two generators. So find the most economic power generation. For solution, it starts from here. For most economic power generation schedule, we have already derived the relations for that. What are those? DCI upon DPGI times LI is equal to lambda. What is DCI upon DPGI? DCI upon DPGI is incremental fuel cost of ith plant. LI is penalty factor of ith plant, where LI, if you remember, LI is given as 1 upon 1 minus del PL upon del PG I. We have derived all these relations in our previous lectures. So for I is equal to 1 or 2, we have two generators. So DC1 upon DPG1 into L1 will be equal to lambda. Similarly, I is equal to 2, DC2 upon DPG2, L2 will be equal to lambda. Or this implies ICI, incremental fuel cost, LI is equal to lambda, where Li is this. So using this relation, L1 can be calculated as 1 upon 1 minus del PL. Substitute the value of PL. So PL in per unit is given as PLOS 0.5 PG1, 0.5 PG1 in per unit square upon del PGI. I for I is equal to 1, here we will put 1. This is 1. So this is coming out to be 1 upon 1 minus half, 2 times half, 1. So this will be equal to 1 minus PG 1. Similarly, PG2 we may write here for Pg2, first write L2. So L2 will be equal to 1 upon 1 minus del 0.5 Pg1 square, because P1 is given as 0.1 Pg1 square on del Pg2. Here we will put Pg2 because I is 2 now. So Pg1 is independent of Pg2, so this will be 0. So this will be 1 upon 1 minus 0, that is equal to 1. So we have evaluated L1 and L2. IC1 and IC2 are given here. IC1 is 10,000, IC2 is 12,500. So for most economic power generation schedule, we may write IC1 L1 is equal to IC2 L2. Substitute the values using this relation, this. So substitute the values, we will get, this implies IC1 is 10,000 times L1 is evaluated as 1 upon 1 minus Pg1 is equal to IC2 is given as 12,500 into, this is L2 is calculated as 1. So this implies all calculations are being done in per unit values. So send this to that side. So we will get 1 minus Pg1. This will be equal to 10,000 upon 12,500 upon 12,500. These two 0 got cancelled. So finally we may write 4 upon 5. So this implies, send this Pg1. Pg1 will be equal to 1 minus 4 upon 5, that is 1 upon 5 per unit. So base value is given as 100 megawatt. In problem it is given 100 MVA, sorry, 100 MVA base is there. So the actual value of Pg1 will be equal to 1 upon 5 per unit into 100 is base MVA. So this will be equal to 20 megawatt. So we have evaluated Pg1 as 20 megawatt. Now our next step will be, let us calculate the loss PL. So PL is given as this 0.5 Pg1 square per unit values. See there, 0.5 Pg1 square in per unit. So you may write 0.5 Pg1 per unit square. That will be 0.5 times, what is Pg1 in per unit? 1.5. So 1 upon 5 square. This will be equal to 0.5 into 1 upon 25. So finally we will get, here we may write 1 upon 50 per unit is equal to 100 MVA base. We may write 1 upon 50 into 100 is equal to 2 megawatt. So we have Pg1, we have calculated PL loss, we know the demand, so directly Pg2 can be calculated, that is PD demand is nothing but equal to Pg1 plus Pg2, Pg1 plus Pg2 minus PL. This implies this is given as 40 megawatt. 40 megawatt. So this implies 40 is equal to Pg1 is calculated as 20 all in megawatt plus Pg2 minus PL is calculated as 2 megawatt. So this implies Pg2 is equal to 40 minus 20 plus 2, that is equal to 22 megawatt. So these are the values of Pg1 and Pg2 for most economic power generation schedule. Thank you very much for watching my videos. In case of any doubt, you